Hello, I'm Bob Palmer from NS2. We are a U.S. corporation staffed by appropriately credentialed U.S. citizens, which delivers the innovative software solutions that are the result of the multi-billion-dollar annual research and development investment of SAP, the world's largest enterprise software company. Our topic today is to discuss how machine learning and predictive analysis can be brought to bear on the challenges faced by the missions of defending the homeland and of national security. Understanding of data has advanced since the data warehousing revolution of the 1990s. At the baseline is raw data. When context is added to data, it becomes information. With the advent of business intelligence tools, we added the ability to, quote, slice and dice and visualize your information in different ways, according to the analytical need, and at that level, you can achieve situational awareness. Now, at the cutting edge is the ability to do predictive analysis, to get to the left of the boom, as they say. These use a type of math and a software technology called machine learning. When I talk to organizations about where they are on this maturity model, most will admit that they're closer to the bottom than to the top. Most are struggling to get to the level of situational awareness. But what does machine learning and predictive analysis really mean? There's many overlapping terms that are used to describe this type of data processing, and there's a lot of buzz around it. My goal for the next few minutes is to help make clear what the nature and potential of this technology is, and perhaps to get you thinking about how it might be useful in your particular mission or business area. In a traditional computer program, the programmer tells the computer how to process the data step by step. Then that program is executed and an output is produced. Just like if you write a formula in Microsoft Excel and run it against your spreadsheet, you know what you want to compute, and the formula is static unless you change it. What is different about machine learning is this. The data itself is used to alter the program. That's what the learning means in machine learning. The computation that you're doing on the data can actually be altered by the data you pointed at. So we say that the program learns from the training data set. Humans still write the program, but they do it in such a way as to allow the specific data being used to alter the computations that are executed. What they're trying to do is to build a mathematical representation of the relationship between data elements, a symbolic picture of reality expressed as probabilities. They call this set of formulas a model. Mathematicians will recognize the Bayesian theorem in the graphic. It's the math behind one of the major types of the many hundreds of machine learning formulas which are available to data scientists. The data scientists train the model on a known data set, such as a set of known bad actors, or they can train the algorithm to recognize words, to do what is known as natural language processing. Then they point that trained model at a test data set to see if it correctly characterizes the nature of the observed entities. They evaluate the accuracy of the model by looking at the output in what they call a confusion matrix. They want the model to find the greatest number of true positives and the least number of false positives in the test data, and vice versa. So the data scientist tunes the model and runs it again and again until they're happy with the output. But they also have to be careful not to tune the model too closely to the training data, or it won't find a thing when they use it with real-world data. That's known as the problem of overfitting the model. This is why experienced data scientists are so valuable. There's a subtle art to tuning the model, but not overfitting it. Finally, after tuning, they turn the model loose on the real-world data and hope that it produces insights and actionable knowledge. So, that's a summary of what the term machine learning really means. There are many different types of machine learning algorithms which can be brought to bear on your data. They can be used to uncover hidden relationships or to discover root causes for phenomena. Machine learning can be a tool to help analysts find the non-obvious relationships in data at high speed when time is of the essence, or to derive meaning from big data at a scale that's just not possible without automation. Regression is a type of math that seeks to predict future values from past values. You may not realize it, but I bet you've studied a lot of regression output recently. Think of the hurricane storm track graphics on TV. The cone of uncertainty is the probable progression of future locations. Regression has obvious application to weather forecasting. But couldn't this type of algorithm also be used in the mission to give a possible location of an adversary based on terrain and past movement? Clustering, classification, and association algorithms seek to assemble groups in the data that are most like each other and most different from all the other groups. We can think of a mission use where you'd like to process a large amount of data to find which entities should be grouped together. How about discovering potential bad actors based on features that are derived from a data set of known bad actors? Decision trees, also known as rule learners, are used to divide data into smaller and smaller portions to identify patterns that can be used for prediction. They're often used in the commercial world for credit scoring, diagnosis of medical conditions, or marketing studies of customer churn. In the mission, decision trees could be used to help analyze courses of action, what is most likely to occur and what is most dangerous. Or, in the cyber domain, they could also be used to identify anomalous behavior to help discover external attacks or insider threats to your network systems. Another type of algorithm used for predicting behavior is called market basket analysis. It's actually named for the original use case, which is analyzing point-of-sale data to understand which things are purchased together. This is where we get the classic example of the relationship between diapers and beer. Analysis of sales receipts can tell us that when the wife sends the husband to the store at 11 p.m. to buy diapers, he also buys a six-pack. Therefore, put the beer near the diapers. Basically, market basket analysis says if a given entity has feature A as well as feature B, that implies that it might also have feature C. Can we think where this type of logic could apply to the mission? How about in helping to predict self-radicalization? In neural network algorithms, the data is processed in packets that are analogous to how dendrites and neurons connect in the human brain. At each mathematical node, the weighted inputs of the data are summed together, then they're passed on to what's called an activation function, which measures whether or not the input should be passed on to the next mathematical neuron. The neural network learns because the weights of the connections are strengthened or weakened based on the exposure to the input data. Now let's take a look at a demonstration of a machine learning software tool from SAP. It's called SAP Predictive Analytics. SAP Business Objects Predictive Analytics is a software tool that's comprised of three major applications. It has a data manager, which allows you to perform extract, transform, and load jobs from data sources in order to group together and integrate data from multiple different sources for analysis. It has an automated analytics capability which empowers non-data scientist and non-mathematician subject matter experts to perform predictive analytics on data. In effect, it democratizes data science. And then it also has the expert analytics tool, which is where experienced data scientists would have very granular control over the analytical process without the automated functionality. But today, let's run a job using the automated analytics tool from SAP. So I can do a classification or regression model, or a clustering algorithm, or a time series analysis, or a decision tree type association rules model. So let's do a classification algorithm. I've got a data set, and I can choose from data sourced from any database of any kind of relational database management system of any brand that's available using ODBC connectivity. Or I can do SAS Institute files, SPSS files, IBM SPSS, or Excel worksheets. So database, flat files, or any other type of application file could be used. Now I've got a data set here, which is student data I got from UC Irvine, the University of California at Irvine, for their Data Science Center of Excellence. And when I look at that data, I import it quite easily by connecting to what I have on this machine as a flat file, and I hit the Analyze button. And now SAP Business Objects Predictive Analytics looks at the metadata, the labels on the data, and decides what the data types are and how they're stored in the data set we're going to analyze. And it identifies data either as a string or an integer. So a character string like a label or an integer. And then it could either be a continuous number from an integer from 1 to infinity, or it could be a label, a nominal named value. So we could check this here to make sure that our tool has indeed identified correctly the data the way we want it to be analyzed. I can hit this button here to actually view the data. So let's take a look at what this data set is that I got from UC Irvine. We can see that it's about education and training. So I have a course name, an instructor name. I've got a student ID number, the gender of the student, where they're from, what their highest educational level was, whether or not they come from a deprived census statistical area in terms of the percentage of deprived score based on the government algorithm actually, what their age is, the number of times they've tried to take this course in the past, what their load was, how many credits they're taking during the period, whether they self-identify as having a disability or not, then the year and the actual term, whether it was the October term or the summer term. And here's the variable that we're going to be trying to predict. Did they pass or did they fail the course? And this is just a row counter number that our software puts on the back of the data set. So now, given all that, I can run this, choose which of the variables I'm going to use in this regression algorithm. I don't think I need to use a student number as a part of the computation. It's a randomly generated number that comes from the organization, the institution of higher learning. So I'm not going to use that, and I don't need the row counter number in our algorithm. But I want to use the course name, the instructor name, the gender, etc., all as part of the algorithm to decide, can we predict here whether the person failed or passed the test, the course. So let's take a look here and go ahead and generate a model from the data using the algorithm of a robust regression. So now the computer is assessing all the data in the slightly less than 4,000 students, more than 4,434 students I had in this data set. And if I look at the output from that model, I see that it's not a bad fit. And here's how you assess that in the profit curve. The red line, this diagonal line, is your I just guessed and flipped a coin line. This is the 50-50 line. If you were just guessing without any evidence or any algorithm at all, you'd get that line probably. The green line would be if you had magical knowledge, pre-knowledge of the outcome. And this blue line is our actual performance of our model. So it's pretty good. This bluish shaded area here is how much better the model did than just the random 50-50 line. And then we can examine here what were the most contributive variables. So we see that instructor ID, the instructor name, which instructor it was, did factor in to the algorithm being able to decide whether or not the person passed or failed. The year and the term, was it the summer or the winter term, did matter. The next, in terms of contribution to the outcome of the algorithm, was how many other credits they were taking, followed by their age. And then much lesser in terms of contribution to the outcome was the number of previous attempts and whether or not they were from a deprived area. Now, I can also output this at the press of a button to a PowerPoint slide. So I can now share and disseminate this information with my boss or the rest of my analysis team. And you can now type in here, what your rationale was for this test and what your recommended outcome should be in terms of ameliorating a problem that you've identified, etc. And then here is the profit curve to talk about how successful the model was, what its predictive power was, and what the confidence was versus the test data. 0.97 is pretty darn good. 3 out of 5 stars. What was the most contributive? What was the least contributive? Variables, etc. And all this can be part of a briefing now. When I also look at this, I can take a look at the confusion matrix to see how my algorithm did. Let's look at all of the data. I think it was 4,443 in terms of numbers. Now I can see out of the total data set in my confusion matrix, the times that it predicted no when it really was a no for fail was 1,356 times. However, unsuccessfully, the algorithm in the model predicted yes, they would fail 413 times incorrectly when they did not fail. As far as when it predicted that they yes would fail, it did predict that correctly 2,257 times out of the 4,000 times, but was incorrect 417 times. All in all, not too bad of a model in terms of the automated capability. Now, experienced data scientists could go further with this, use the expert analytics tool to tune the model even further. But I think this is an exciting combination of predictive analysis machine learning that could be accessible to non-mathematician, non-data scientists, subject matter expert type analysts, who after all understand your mission better than anyone else does. So that's an overview of SAP Business Objects Predictive Analytics. We emphasize the automated analytics part of the tool and can also at a future time discuss the expert analytics for the right type of user. Thank you very much.